Okay, recording is now in progress. So I have identified two different times that we can try and meet for Action Center. I know that this is just from the outset, there is not a time that everyone is going to be able to meet. Y'all are busy, you're taking other classes, you have families, you have jobs, you have other things that pull on your time outside of this class, and I get that. My goal here is to try and find a time that probably the most people would be able to meet and a time that's convenient because we would follow right after class. I'm going to hold 2 Action Centers a week. One is going to be right after OCHEM 2. That's going to happen. So OCHEM 2 is 3223. That's going to happen on Wednesdays from 10 to 10:50. We did not hold one today because it was the first day of class or first day of lecturing material. I am going to try and hold ours on Mondays from noon to 1. Yes, that is right over top of lunch. That is not ideal, but this class ends at noon. And so what we could do is finish class and then go over to the Action Center for Monday. You can come to either one of these. My hope is that putting this right after our class, the majority of people would be able to go there. But if you can't make it from noon to 1 on Mondays, or you don't want to go from noon to 1 on Mondays, you're also welcome to join us from 10 to 10:50 on Wednesdays. The reason I am stopping at 10:50 on Wednesdays is I have to be here with you all at 11, right? So you're kind of in a good situation of both the Action Centers hug this class, right? It's either right before class or right after class on Monday or on Wednesday. If you cannot make either one of these times, what I recommend is getting in touch with some of your classmates and finding a time that you can meet outside of class. Go to a coffee shop, you can meet on campus somewhere, and work the Action Center just in your own time. Action Center is voluntary, and it is not meant to be like homework. You have homework, right? So you have individual practice. Action Center is a time for you to be able to work with your peers. These are times I will be there to help move things along, but I'm not going to be sitting with your group working through the problems. I'm going to be sitting at the front of the room trying to ignore you as much as possible so that you talk to each other. So if you can't make one of these times or you don't want to be there for one of these times, you're not going to be penalized. Again, the worksheets are posted on Blackboard, the keys posted on Blackboard, so you will have access to all this material. I don't have one posted currently because we don't have enough material to talk about one yet. So our first Action Center is going to be Monday, next Monday, from noon to 1. We're going to meet in BASC 248. That is on the second floor of the science building next to the organic lab. So I think probably several, we haven't had that lab yet, but I think probably several of you are in the organic lab. It's just down the hall from there, or apparently genetics is on the second floor now. It's near the genetics lecture hall as well. Questions for me about Action Center? Yeah. So if you go to the Wednesday one, how many of you are interested in for Wednesdays? Okay. That many people from your class will be there, possibly. The part that's no fun is if you show up at an Action Center and it's just you, because then it'll be just you and me, and I'm fun to do a homework with, but not the same as your peers. So ideally, we'll get at least 2 people at each one of these things. There's going to be a majority of OCHEM 2 students in there, but that can be helpful too, because you can be like, hey, what's that monster making you guys do? And how's the class going? Action Center is about you guys talking to each other. In this space, I'm all egotistical. You're looking at me. I control the room. Action Center is to say, hey, let's get me out of the picture a little bit more. Okay. Let's talk about organic chemistry. This is Chem 3123. And I think a good place to start is chapter 1. Chapter 1 is about structure and bonding. If we are going to talk about organic chemistry, probably the first thing we should do is define organic chemistry. Can anybody tell me what is organic chemistry all about? Yeah, the study of carbon. And really not just carbon. Carbon itself is just coal or diamonds. Pretty crazy that it's the same thing, right? Same atom makes up either coal or diamonds, slightly different materials. It's the study of carbon-based compounds. There are just shy of 120 elements on the periodic table. And we're going to spend, for some of you, 2 semesters, an entire academic year talking about one atom. That's pretty weird, right? I have periodic tables on either side of the room. Look at all those boxes. There are atoms for days. The most important of those atoms, I think, is carbon. And the reason is it's one of the most versatile. Things like hydrogen and helium, they are really important. They're really abundant, but they only do a couple different things. Carbon is responsible for methane, natural gas, and DNA, us. Carbon makes up me and the plastics in this on this tablet, and the chairs you're sitting in, and the screen. All the same materials are coming from this one atom. So there's something special about carbon. We're not actually going to talk a lot about carbon as an identity. We're going to talk about the electrons around carbon, because what this class is really about is how does carbon make bonds to other things? That's where the magic is. And so for carbon making bonds to something else, we have to talk about where are the electrons. That is section 1.2. You're going to see me, oops, still in blue. You're going to see me in class write circles like this. That is chapter 1, section 2. So you can always know where I'm referring back to in the book. I'm going to do my darndest to follow the book because I think it's organized pretty well. There's a couple times when I won't do that. So I'll try and give you a foothold here so you can go back and find in the text where I'm at. Section 1.2 talks about atomic structure. And the most important part of this that we're going to talk about are something called orbitals. In an atom, the Bohr model of an atom, we have in the center of this thing neutral particles, those are zero charges, and positive particles, those are called neutrons. And then floating around the outside of this, we have electrons. I'm going to abbreviate electrons as a lowercase e with a superscript negative charge forever, because my handwriting's terrible, and anytime I can abbreviate is another time you don't have to read more letters from me. Which, by the way, I saw on someone's card. Who's my lefty in here? All right. I've got a lot of, couple of us. What? I've had a class of 55 students with no lefties. So I feel your pain and your struggle. I'm looking forward to also trying to decipher your bad handwriting too. I'm sure your handwriting's lovely. These electrons, where they're at is really important for us. So this is kind of a simplified model of the electron just floats around the outside. We know that those electrons are actually in a sphere. So I'm going to simplify the nucleus as a little dot. And I'm going to put, if I could shade it, I'll just put lines across here. This is what we would call an electron cloud. You're going to see me put electrons in red a lot in this class. They won't be the only thing that's red, but I'll try and put them in red as much as possible. That is, of course, the nucleus. If that cloud in a sphere around the outside was a three-dimensional object, we would call it what kind of orbital, Jen Kimmers? Remember when your Gen Chem professor was like, hey, there's things in the electrons around the outside? We use some letters to describe these things. This type of orbital is called an s orbital. I have now used this word a couple times, orbital. What the heck is an orbital? Anybody know? I have good news. Organic chemistry is famous for not using a lot of math. If you're a math person, I apologize. This is not going to be your course. For most of us, math is a thing that we are forced to do, and it doesn't necessarily light us on fire. Orbitals, so the thing I was going to bring up is what we do to get around having to do a lot of math in organic chemistry is we draw pictures. So instead of a mathematical equation, I'm going to draw a picture. An orbital is a mathematical prediction of where you will find electron density. So when I say that electrons may occur within this sphere, there is some math that I can use to determine where the electron probability is going to be. Orbitals, or a math model. I'm going to put this in a different color so it's not blue on blue on blue. Orbitals are a math model of electron density. Around a nucleus. Well, they can actually be in different places, but we're going to talk about them around a nucleus. If you're an electron, where do you want to be? Next to other electrons or next to the nucleus? Nucleus. We're going to put ourselves in the perspective of electrons pretty frequently in this class. Things that make electrons happy are going to be beneficial. Those reactions are going to occur quickly. Things that make electrons unhappy are going to not occur quickly. So if I can go from a very uncomfortable state as an electron to a place that's close to nuclei, I become much more stable. The reaction is going to proceed that way. Electrons love to be in s orbitals because what that means is you have a nucleus here and you get to be all over it. Several of you have identified being fans of sports. As a football reference, you are a really good defensive lineman if you're in the s orbital. Here's the quarterback. You get to be all over this thing, right? You have good contact with the thing you want to be closest to. You might be familiar, though, that there are other positions you can play in football. There are other positions we can put electrons around here. One of those is I'll just draw it back up here so we have them on the same page. The s orbital, like I said. I'll come back to these lines here in a second about what they mean. But I can also put electron density above and below the nucleus. Like this. Sometimes this is called a dumbbell shape. I don't work out very much, but I've never lifted a dumbbell that looks like this. I think it looks like two balloons that are stuck on top of each other. What kind of orbital is this? A p orbital. Right here in the middle of the p orbital is the nucleus, but it's also a region where you will not find any electron density. Does anybody remember what that area is called, where there's no electron density? Sometimes you see it shown as like a dotted line. It's called a node. Equals an area with no electron density. You all are electrons. How do you feel about nodes? You guys are people. How do you feel about people telling you what to do? Not good. Don't like it, right? Well, I'll leave my politics out of it. I don't like people telling me what to do. I'm all for society and people all getting along, but if you put a lot of rules on me, I don't like it. Electrons are the same way. They do not like to be told where to be. And in particular, look where the node is in this molecule or in this atom. The node is right at the nucleus. Well, you're an electron. That's where you want to be. And I'm saying, hey, this spot, this like super comfortable spot for you, you can't go there. So the electrons do not like that. For that reason, p orbitals are less stable than s orbitals. A way we're going to refer to this is a p orbital being less stable is also going to be called higher in energy. So this is a weird relationship that doesn't always click right away. High energy means less stable. Low energy means more stable. I have some crazy cousins. You probably have some people in your life that are this way as well. If my crazy cousins call me on a Friday night and they're like, yo, Nate, you want to come out? It's 2 a.m. Let's go party. My answer is no, because they're going to prison. They are high energy. They're going to go do something stupid. They're going to meet Tulsa's finest here pretty soon. Your friends who call you on a Wednesday and they're like, hey, do you want to come over for board games, like for brunch? They're fine. Those are your rock solid people you can count on. Low energy, more stable. High energy, less stable. Same thing is true for molecules. The s orbital is lower energy, or sorry, more stable. And thus lower energy. That makes sense? About my cousins? Okay, so not only do we have these two different types of orbitals, a sphere, happy, and the dumbbell, unhappy, but we also have shells of how these electrons can get around an atom. In the first shell, you have just an s orbital. In the second shell, you have another s orbital, but it's further out. So a way of visualizing this is if I have an atom, a nucleus here in the middle, I can make an s orbital around it in the first shell. In the second shell, I make another s orbital, it's just bigger. And within that space, I also can then add a p orbital. So we need to start drawing these out a little bit. I'll do it over here. We're going to arrange these according to energy. So capital E is energy. Right? In the first shell, I can draw a line representing the electron density. And I'm going to put 2 electrons in here. We represent electrons on these little models, what we call electron configuration, by half arrows. So when I put a half arrow pointing up, that means 1 electron. I'm going to put a half arrow pointing down, it means a second electron. So there are 2 electrons in this shell. So let me write this out so it doesn't look like an I. There are 2 electrons in the 1s orbital. I drew a line down here. That's the first shell. The lowest possible energy level is an s orbital. So I put 2 electrons in there. Sometimes you'll see that referred to as 1s, and we'll put a 2 up there in the corner. I'll leave it off for now, but you probably have seen that in Gen Chem where you write 1s2, 2s2, 2p6, all that. That's what we're talking about. In the second shell, let me spread these out a little bit. I'm going from the first cell to the second shell higher in energy. Why might the second shell be higher in energy than the first shell? It's less stable. Why? What is that? Further from the nucleus, right? Think of the nucleus like a campfire. If you're in the first shell, you are right around that campfire. It's nice and warm. Not right now, right? Let's make it cold. Go up north somewhere. You want to be as close to the fire as possible. The farther you get away from that fire, the less you feel the fire. The electrons feel the same way about the nucleus. As I go from the first shell to the second shell, I'm getting farther away, and the electrons are like, but wait, I like it was cozy. There are going to be 2 separate types of electrons, 2 separate types of orbitals in the second shell. This was 1s. This is 2s. Both are s orbitals, but the second shell is higher in energy because it's farther away. On top of this, I'm going to draw 3 lines that are next to each other that represent 2p. That means p orbitals in the second shell. Each one of these can also take up to 2 electrons. So drawing this out, I'm saying that the first shell has 2 electrons, 1s2. The second shell has 2 electrons, so 1s2, 2s2. And then I can put 6 electrons in the p orbitals, 2p6. And we're not going to talk about it in those terms where we write 1s2, 2s2, 2p6. But we're going to use this to start out our understanding of carbon and then really mess with that picture because it gets more complicated than just this. Why did I put 3 lines for p orbitals? It said a p orbital looks like that. Because you can add more electrons to the p orbitals because it's not just that shape. But then like my hand is the node, and then these are the lobes of the p orbital. A p orbital can exist in the y plane, so straight up and down. It can exist in the x plane, horizontal, and in the z plane, because we're talking about 3-dimensional things. This is going to be a common thing we deal with in here. I have a flat piece of paper or a flat board to write on, and I'm trying to convey 3-dimensional information for you. So that's going to be a challenge of something we deal with. This is the first time we're going to talk about that. p orbital, what we call py, px, pz. These are equal orbitals, but there are 3 of them. I don't talk about spheres that way because it's just one. You turn a sphere and it's still just a sphere, right? So we refer to this when you have 3 orbitals that are equal in energy as degenerate. Degenerate always sounds pejorative to me. It sounds like a bad thing. You degenerate. Degenerate here means equal in energy. You guys with me so far? Feeling very gen chemmy right now? It's going to be that way for a little bit. Okay, what I want to do is focus on individual atoms now. So this is just how many electrons I can fit in each one of these orbitals. Let's use the periodic table to start filling out electron configurations for particular atoms. This is going to be section 1.3. On the periodic table, there is a bunch of information. Each atom gets a little card. They get a symbol. Those are good for impressing your friends and for trivia night. Otherwise, just have a periodic table that you can look at. I had a graduate course where I had to memorize the periodic table. Ask me if I still have the periodic table memorized. No, I don't. It was a waste of time. But hydrogen has a symbol of H. You'll find a number on top, and you'll find some numbers on bottom. What's the number on top? The atomic number. What's that tell us? Correct. The atomic number lets us know the number of protons. Not as helpful for this class because we're interested in the number of electrons. Good news. Every atom on the periodic table, as given, is neutral, which means if hydrogen has 1 proton, it must have 1 electron because you have to have a plus and a minus balance each other out. So we're going to use this number to tell us how many electrons are present. They're organized by atomic number through the protons, but will tell us both the number of protons and electrons. The number of protons equals the number of electrons in a neutral atom. How about this number down here? The atomic mass. That's super helpful for when you're actually doing chemistry. So in the lab, we will use the atomic mass. It is written in grams per mole. That's if I want to take an amount of stuff. So if you gave me a pile of carbon and I wanted to know, oh, how many carbon atoms do I have? I need the atomic mass to figure that out. But we won't use that number in here very much. That's actually taking this thing and using it in the lab. We will use the top number much more in this class. If I wanted to draw an electron configuration for hydrogen, how many orbitals should I draw? 1. Let's put it down here. That orbital would be which one? 1s. How many electrons go into that 1s orbital? Just 1, right? Because a hydrogen atom is neutral. We're going to use that number to put just 1 electron here. This is the electron configuration for hydrogen. It lets us know how many electrons hydrogen has and where they are. That's super boring. By the way, this whole thing that I just drew for you is physics, doesn't move beyond hydrogen very much. So I have friends who spent 8 years writing PhDs over this, where this electron is and how stable it is. For me, this is as deep as we're going to get into the subject. Hydrogen has 1 electron in the 1s orbital. Let's compare that to carbon. Carbon has a 6 above it and weighs 12 and some change. Those numbers will kind of change depending on what periodic table you're looking at. The 6 tells us that we have 6 protons in a carbon nucleus. There's also 6 neutrons. And importantly, 6 electrons. Let's try and keep these the same shape. Can I put 6 electrons in a 1s orbital? No, I can't. So I better get creative here and put not only a 1s orbital, but also a 2s orbital and then some 2p orbitals above it. The way I'm going to put these 6 electrons over here is I'm going to start filling from the bottom up. I'm going to put 2 here. I'm going to put 2 here. And then, so I've got 1, 2, 3, 4, 5, 6. The remainder are going to go up here. How did I know to put them like this? There are some rules for how we fill out electron configurations. Rule number 1, we're going to fill from the bottom up. Now is a good time for me to check on languages. I speak only English and poorly. So I'm jealous of you who speak multiple languages. Does anybody in here speak German? Excellent. I can butcher the German language. Anybody in here speak French? Partially. Okay, then you can partially give me a hard time. Any Russian? Old school chemistry is in one of those 3 languages: French, Russian, or German, because the French, the Russians, and the Germans were doing this well before America was a country. Late chemistry, we took over. We're rock stars. If you look at Nobel Prizes, the last 100 years, us. All the ones before that, not us, because we were still trying to figure out like how to do the New Deal and build highways and stuff like that. Why am I talking about that? This principle comes from the German word from the bottom up, and it's called the Aufbau principle. I'm a big old etymology nerd. So that is the study of where words come from. I think language is really fascinating, and especially English, because English is a messy language. We steal from everybody in multiple ways, but especially with our language, right? So Aufbau here is a German word, which means bottom up. So when you're filling in electrons, it makes sense, put the electrons in the most stable orbitals first, and then you go from there. I didn't take 6 electrons and just put them in the p orbital, because then you would say, well, why don't some of them go to lower energy orbitals? Rule number 2, put 2 electrons in an orbital. But give them opposite spins. We're not going to talk too much about what this is, but very oversimplified, that's what these arrows are. The electron on the left is what we call spin up. The electron on the right is what we'd call spin down. It means that the electrons can occupy the same space, but not become one another. Remember, electrons really love nuclei. Electrons do not love each other. And so it gets too crowded. If I put 2 electrons in here, we have to have kind of matching personalities to get them to occupy the same space. When you all came in to sit in this lecture hall, you didn't all sit here in the corner, like shoulder to shoulder with a bunch of space over there. That would be weird, right? But if you did, it would let me know that you were all best friends. You had personalities that matched appropriately. Some of you would be spin up and some of you would be spin down. Too many spin up people sitting next to each other starts a fight, right? We just get crowded and uncomfortable. So don't worry about there's a lot of physics behind what this spin is, but we're going to represent these electrons with these half-sided arrows. The final rule here, oh, sorry. Anybody remember what this opposite spin thing is about, or whose rule it is? Very exclusionary. Pauli exclusion principle? I'm calling all your Gen Chem professors and letting them know. The Pauli exclusion principle. If you want a stupid way of remembering this, I always think Pauli wants a cracker exclusion principle. I don't know why. And then the final one is if you have equal orbitals, they are half filled first. Up here, these are my equal orbitals. These are my degenerate orbitals. I filled in one electron here and one electron there. Why? Electrons do not want to be near each other. So if I can spread them out a little bit more, it is stabilizing for the electrons. So I'd put one here, one here. If I added another one to my system, it would go here. If I added another one, then I'd go and start pairing them up together. That's called Hund's rule. The off-ball principle, Pauli wants a cracker exclusion principle, and Hund's rule let us know how to fill out electron configuration diagrams. This is an electron configuration diagram. So much fun. So much fun. Tell me more. All right, we need to know where the electrons are in this base model, because as it turns out, we spent like a couple centuries, we spent a couple decades, a long time, thinking this is how electrons were around carbon. And then this dude, whose name is escaping me, German guy, figured out that the electrons don't sit this way. So we need to know where the electrons were assumed to be so we can complicate the picture a little bit later on. Before we get there, let's talk about what we're going to do with these electrons. Oh, last thing too I want to bring up. These guys over here, and the 2s and the 2p are called valence electrons. We're going to use these here in a second. What's a valence electron? That's right. Valence electrons are the outermost. That's going to matter because we're going to use those electrons to make bonds to other things. Cats have valence hairs. They have these hairs at the edge of their body, and it lets them know if they can fit through a surface or not. So if you have a cat and you really want to drive it crazy, very lightly pet your cat. And it's going to be like, I'm being crushed right now because its valence hairs are all being touched. These are the valence electrons because they are on the outside of the molecule. They are in the second shell. Let's use those valence electrons to make bonds to other things. That topic is called, I'm stalling because I keep seeing pencils move, valence or chemical bonding theory. We have lots of different ways we talk about how molecules form or how atoms form bonds to other things. I'm going to go through a few of these, but common terminology we're going to use is that when two atoms share their valence electrons evenly, we call that a covalent bond. When two atoms share their electron density, we don't call them two atoms anymore. They now are referred to as a molecule. We're talking about organic chemistry, so let's talk about the simplest organic molecule, which is a carbon and 4 hydrogens. And it's called methane. An example of a molecule. Methane has a molecular formula of CH4. So what we need to do to build a model of methane is figure out how many valence electrons do we have to play with to put all our Lego pieces together. To do this, we are going to use the periodic table as a shortcut. So periodic table looks, you don't need to draw this, but you can if you want. Ooh, that's bad. Boom, periodic table. We are going to focus on this area up in the corner, but what you might notice is if you look on mine, there is a 1, 2, and then over here, 3, 4, 5, 6. Oh, I didn't draw this very well at all. You know what? Oh no, not that one. Okay. In this corner, I used to teach this class on a chalkboard and I didn't have to push buttons and my life was better. Here we are. In this corner, you're going to see a couple atoms that we need to use on a regular basis. Boron, carbon, nitrogen, oxygen, fluorine. But KNOF. If you memorize BCNOF and their corresponding numbers, you'll see that there is a 3 above boron, a 4 above carbon, a 5 above nitrogen, 6 above oxygen, and a 7 above fluorine. Those Roman numerals correspond to the number of valence electrons present in each atom. Not the total number, right? Carbon has 6 total electrons, but it has a Roman numeral 4 above it, so it has 4 valence electrons. Every atom in that column also has 4 valence electrons. We'll come back to this later on, but if you wanted to know how many electrons silicon has, it has 4 because it's over here. If you wanted to know how many electrons sulfur has, it has 6 valence electrons because it's underneath oxygen. So for this first bit, while we're learning everything, I encourage you to have a periodic table handy because I know these are not close enough for you to be able to see them very well. These are the only numbers I really need you to know from the periodic table. So the sooner you get this memorized, the sooner you can just ditch the periodic table for all of organic chemistry. Well, we'll get there. Over here, where hydrogen is, there's a 1. So using those Roman numerals, because hydrogen has only 1 valence electron, because hydrogen only has 1 electron, right? Using those Roman numerals, I can count up my valence electrons. Carbon has 4. Hydrogen has 1 apiece, or 4 total. 4 plus 4 equals 8 valence electrons. Somebody learned something really important upstairs just now. They were like, got it. All right, how can we use that? Can I get rid of my periodic table? I know it's a really good drawing, but I'll leave this over here. I'll just get rid of this part. How can we use those numbers to try and build the structure for methane? Well, something you may be thinking about or have heard about previously is that carbon-based structures use carbon as the backbone. So typically what we're going to do is we're going to put carbon as a central molecule. And if I have 8 total valence electrons to put around this thing, why don't I just show them as dots? Because electrons can be dots. They can also be waves. Electrons are crazy. If you study them for any length of time, it is wild. This whole idea of being a particle and a wave at the same time. I won't throw that on you right now, but just heads up, you are here in this room and infinitely everywhere in the universe at the same time. So sleep tight. These 8 electrons can be around carbon. And then what I'll do is just put a hydrogen sharing each one of those pairs of electrons. I have shown 1 carbon, 4 hydrogens, and 8 electrons binding all of those together. I use dots to make the lines, or use dots to make the bonds. This is what we call a Lewis dot structure. Lewis Lewis dot structures are for babies, and you guys aren't babies, you're organic chemistry students. If we draw every molecule this way, it's going to take you forever. Methane has 1 carbon. I'm going to have you draw molecules very frequently that have dozens of carbons. We can't be doing this. It's going to take us too long. So in short order, what I want you to do is get comfortable with turning that picture into this type of picture where we draw lines. Every line here represents 2 electrons. So instead of drawing a dot, we're going to draw a line. These are called line or Kekule structures. But wait, it gets more complicated than that. Because we're going to find out that carbons that have 4 things around the outside aren't flat like this. So the thing I'm drawing on right now can be well represented by this screen, right? It is flat. It occupies just the plane, the XY plane in front of you. But the world is 3-dimensional. I can reach out of this screen. I can reach back into this screen. So we're going to use some lines to show that carbon is actually a 3-dimensional structure. I think I heard someone say wedge and dash. You know what's coming your way. 3 of these atoms, 2 hydrogens and a carbon, are in the plane of that screen. 1 of these hydrogens is coming out at you as a wedge. And 1 of these is going back into the board as a dash. Think of this as like one of those, some of you are a little young for this, but some of you may know what I'm talking about. Some of the first like early 3D movies that they released, they've like made a big meal of this when they'd be like, here comes the 3D object, and they like wave it in your face and you're like, oh wow. And now if you watch it, you're like, you get it. 3D's like thing. A wedge is when you have a hydrogen coming out at you, right? So this hydrogen on a wedge, sorry, let me start out this way. I'm in the screen. I'm a carbon. I have a hydrogen pointing straight at it, flat line. I have a hydrogen pointing off to your right, flat line. On this side of me, there's a hydrogen coming out at you. That's represented by a wedge. And there's a hydrogen going back into the page. That is represented by a dash. Overall, I have a 3-dimensional structure, and I'm trying to represent that in our 2-dimensional plane. This idea of drawing things in 3 dimensions is called stereochemistry. We'll talk about that in chapter 5, but just be aware if you're a sort of person that needs to like have multiple iterations of driving to a place because you keep getting, if you get lost a lot in new places, you have a problem with spatial orientation. It means you're very talented at other things, but you have a hard time of taking 3-dimensional information and putting it into your head. Chapter 5 is going to be rough for you if you're one of those people. That is most of us. Turning flat things into 3-dimensional things is hard for us. But just be aware, we're going to be talking about a lot of 3-dimensional things. Everybody seen something like this before? Lewis dot structures? Maybe not line structures. Some schools talk about that, some don't. We'll start using these pretty rapidly. When you're putting these together, there's a lot of different rules we need to use to make sure we don't go off the rails. One of them is called the octet duet rule. And that is that almost all atoms, got to put like a caveat here because there are some atoms that break the octet rule, but almost all atoms are most stable with 8 valence electrons. Why? Why is 8 a magic number for us? It's 2 on each side, but what's that do for us? Remember, let's think about it for carbon. 2s, 2p. How many electrons can I put in all these orbitals? Total. 8. 8 electrons fills up every one of these orbitals. meaning everybody's got a place to be. What kind of atoms on the periodic table have this kind of configuration? The noble gases. Now notice when I told you I wanted you to memorize the upper part of the periodic table, I said boron, carbon, nitrogen, oxygen, fluorine. There is an atom to the right of fluorine. It's neon. Why didn't I talk about it? Because neon is boring. Neon does not make bonds to other things. When neon runs into other atoms, it goes, ooh, you know what? I'm all full on electrons. I don't need you. Can you just go away, riffraff? Right? All of the atoms, helium, neon, argon, all those guys make pretty lights. Those are the neon signs that we see. If you run electric beam through them or electric charge through them, they glow. Those are atoms in those tubes that make the neon signs. They do not make bonds to other things, and so they're not very useful to chemists. Carbon does, though. The goal of every atom is to achieve a noble gas configuration. Oops. Well, why not? That is, all of its orbitals get filled up. Hydrogen would love to do that too, but hydrogen's little. My son is 4. He has this tiny little backpack. It's the cutest thing ever. I can't put 8 electrons in the backpack. He's too small. I can put 2 electrons in the backpack. I'm going to apparently use every color for this definition. Let's go back to blue. The reason that hydrogen can only accept 2 electrons is it has 1 orbital, a 1s orbital. So you can't possibly put 8 electrons in there. But hydrogen is full if it gets 2. Let's look at this with an example that doesn't have any carbon in it. Water. Molecular formula of water is H2O. How many valence electrons are coming from my hydrogens? 1 each, 2 total. Yeah. How many from oxygen? 6. Very good. Who says? You do, and Mendeleev do to put the periodic table together. Comrade had some good ideas. 6 plus 2 is 8 valence electrons. So if I'm going to draw this out, H2O, I think what I'll do is put a hydrogen and 2 electrons, and then another hydrogen and 2 electrons, and then I got an oxygen I need to account for. So 2, 4, 5, 6, 7, 8, water. You guys don't like my drawing? I worked really hard on it. What's wrong with it? I should probably put the oxygen in the middle. Why? It is more stable. Why? I'm like the most annoying toddler. Why? The octet rule. How many electrons currently are around my oxygen? 6. 6, you may know. I'm not good at math, but 6, not 8. Different numbers. How many electrons are around this hydrogen? 4. Bad, right? We've got an upset hydrogen. We've got an upset oxygen. That's no good. So this is probably not a very good Lewis dot structure for us. Let's try again. Maybe what we should do, because oxygen is a bigger atom, is we can put numerous electrons around the oxygen and then put hydrogens on the outside. I would end up with these weird guys. What's this called? A lone pair of electrons. But if I do it this way, I have 2, 4, 6, 8. Who do we appreciate? 8 electrons around the oxygen, and 1, 2 around this hydrogen, and 1, 2 around that hydrogen. I have satisfied the octet and the duet rule drawing oxygen this way. Remember, that's not how this is a Lewis dot structure. That's not how we're going to be in the business of typically drawing it. So you're going to see me draw water like this. That's a Kekulé structure for water. We will leave it there for now and pick up with section 1.5 called valence bonding theory on Friday. Have a good rest of your day. Where does the time go?